100 MB of file, 4 KB of buffer, what will break? That's the question. So by the end of this video, you will know exactly why the duo or combo would actually cook your CPU and what's the hardware secret feature that actually saves it. So let's wire up the actual reality. So the whole agenda today is we'll be understanding the computer system organization and why we are learning that, so that going forward with the playlist we could understand what is actually happening at the hardware level. Nowadays we know that there are like one or more CPUs in our system, and also we have device controllers and shared memory, and all of is connected via a system bus. I know this will sound a hell lot of jargons, so don't think much, forget whatever I said. We'll go one by one so that you could understand what is actually happening, and I'll keep it as simple as possible. So yes, let's start. Out of all the jargons which we talked right now, the very first one which we will be studying is system bus. Now what does system bus is all about? So it provides a functionality, or think of it like some central highway that allows multiple components of the computer, or like multiple components of the computer, to communicate between each other. So if any of the components wants to talk, they'll need to use this central highway. Now let's write that. Before moving towards all the three different type of system bus, which like see, system bus provides three different functionality, or we have three different type of roads where all the information is being passed, and what kind of information is being passed on which type of road, we'll see it. But let's first try to visualize how it looks on the motherboard itself. Now we won't be drawing the actual motherboard, but we'll try to depict the logical representation of it. So assume this rectangle as CPU. Now this one is disk controller. Now we'll keep limited components in the diagram so that we could focus on system bus rather than all the components at once. This one, assume this is RAM or shared memory. Now for all this components to communicate, we have system bus. Let's first draw it and we'll talk about it then. Now there are three type of roads which we discussed. The very first one is address bus, then data bus, and then control bus. So if we want to depict that also, so let's do that. So the very first one which we could depict is control bus. The second one which we could depict is address bus. So with which color we should depict it? Or let's say we go with green. And we say it is address bus. Control bus. Now the very last one is data bus. We'll see what purpose it serves. Now we draw the logical representation of it. Now we'll be seeing what each thing like actually is responsible for. Now starting on with address bus. See, address bus is strict one-way street. What it means is only CPU can drive instruction on it. Let's suppose when CPU wants to like read or write on some specific location or do any operation on specific location, so it will have to dump the specific location of it, and that the channel which it will be using to do it is the address bus. If you want to think of like dropping some GPS coordinate onto the copper. So the very first thing which we saw is it's unidirectional. The second thing is CPU puts specific location into it. See, we'll see it one by one, and then we'll try to take example and we'll try to like collate it so that we could understand how these things work in like asynchronous manner. Now the second one is data bus. So data bus is a two-way highway, meaning this is where actual package, like it may be some text file, maybe some mp3 file, maybe some pixel, and all those travels via this component. So if sometimes CPU says, oh, give me the data, so another component can place the actual data out here. So it's bidirectional in nature, and actual data is placed out here. Now the third one is what is left? Control bus. Now if you want to think of control bus like some traffic lights. So it will carry the individual command like read, write, or some system clock pulse, and it tells the component exactly when to look at the other roads. And when I say that, what does it mean? So it carry like all the signals from CPU so that it could regulate and coordinate all the system activities, like from memory read, memory write, IO read and IO write. So all these things are happening via this control bus. Okay, if you don't get it also, we'll see an example so you'll get it. And by default, this is also bidirectional in nature. And what it does, it carries individual commands like read, write, etc. Now we will try to see this system bus with a very simple example so that we could understand it properly, all these three things combined. So imagine a customer is ordering something from the bookstore. So bookstore generally have shelf where books are placed, and all those shelf is having dedicated number or like something attached to it, so that customer could say, okay, I need the information from that shelf. So for our case, what we will do is we'll assume that our CPU is our customer, and then our RAM is our bookstore. What you could think is like what you could think in computer terms, similar analogy is like, if you actually, if CPU sometimes wants to like read or load the letter XYZ from like some text file which is actually stored on our RAM, so it will use the same analogy. But in our case, to make things simple, we'll use customer and bookstore analogy. Now, what will happen? As we know, if you want something, so you need to tell them where it is exactly placed. So what should CPU tell? Okay, I need the item sitting on shelf number, let's say for our case 1000. And we have read the address bus. So where it should keep the information, that particular information, although this will be in binary, I need the book on shelf 1000. So where it should be kept? On the address bus. Now, because it's a one-way street, the RAM just listens. It can never send address back to the CPU. So why will bookstore needs to like send those information? Only customer will ask that. Now control bus. At the same time, when CPU is keeping that thing, that particular information on the address bus, what it will do is it will think of like flashing like green light down the control bus and with a read signal. And what does it depict in real life is, oh, hey, hold on, don't pack anything as of now. Right now, I'm just actively buying, so that the bookstore owner could actually give you the book and not the entire package stuff and the bill and all, so that you could see the book, and if you like it, you'll purchase it later. So for our case, this, think of it as like a read signal. I just want to check it. I'm actively buying. I'm not like telling you to pack all these things. And in case we want to pack all those things and we want to take it, so we could have signal write or something in terms of like computer analogy. For our case, read means I'm actively buying. For now, just give me that. I'll later see, I'll see whether I need to buy it or not. So at the same time, when it the address is kept on the address bus, on the control bus, the read signal will be provided by the CPU. And what it does means, what it means in literal ways, don't pack, just actively buying or looking. Now, now that we required some bus, or in our in computer terms, we required some data. So it's the responsibility of bookstore that they actually provide us the data to us. Now the here the role of data bus will come. So what it will do is it will place the actual book or data. So in literal sense, it's more like It's more like bookstore owner is giving book to you. But in computer terms, that is done via data bus. So that's the whole architecture of the system bus. Now that we understood the system bus, so there's a question for you. Actually, two, one of which I'll be answering, and the second one is for you to think and answer it for yourself. So the first one is, let's suppose there is some malware app which actually try to hijack the address bus and flood it with fake addresses so that it could confuse the RAM. So what is the actual physical hardware rule that stops it? So I'll give you 5 seconds to think. You could pause the screen, think for your answers. You have read it. 5, 4, 3, 2, 1. And the answer is the physical hardware layout itself. How? We know that address bus circuitry is like physically printed on the motherboard to only accept the electrical output from the CPU pins. No matter the other peripherals or RAMs are physically present on the computer device itself, they are not capable of like driving electrical signals onto the this address bus. So we read that it's strictly one way. Only CPU can put information out there. No other peripheral device, whether it's RAM or any other component of the system. And the second question is, why do we have central like highway for this? Why can't each device or each component can be connected to each other? So think of all the possible answers for it, and we'll move ahead with like device controllers now. So today we'll be studying device controller. Now, see, our computer's brain works incredibly fast. Like it actually does billions of tasks every single second. But on the other hand, if you see USB stick or hard drive, it is like quite slower or much slower. And in case the CPU had to wait for the like slow drive directly, then in that case our expensive or like a modern computer would slow down to the speed of, let's say, like 2005 iPod maybe. So we need to stop this. So what we need in order to stop this, what we need to do? So we use a middleman chip called device controller, and it acts like protective buffer, and it consists of three different parts. Let's actually build it, or let first visualize it, and then we'll try to learn one by one as we have been doing. So let's try to build it. So let's assume this one as our device controller. Now we'll assume this as our like system bus, which we already studied. And like we'll assume this are as our SSD or like flash. Now inside this we'll see one by one what all this is. CMD, stat, and then this one is data register. Now we also have a buffer in here, and apart from this is just the translation logic. So we'll see what all these things. Let's first draw it. So now we have CMD, which is nothing but command register, and this is like write only register where the CPU drops instruction for disk controller to execute. So see, whenever the computer wants to read or read a file or read some data or anything, it will write the specific command or code directly into this box, this CMD box. Now stat is status register, and this is read only register. The first one is write only and this one is read only register. And CPU actually checks to see what the disk controller is currently doing. So it will hold a single bit flag, similar to like if the CPU if the controller is busy, it will say that it's busy. If it's ready to transfer the data, it will say okay, DRQ or something. Or if the operation failed due to some issue, it will say error or something. So we saw that in the system bus how these things are communicating via command. So that particular command will be there on the stat or status register. Now data register, this one is bidirectional register and it is used to move the actual bytes or actual data. So during a write operation, let's say CPU pumps our data into the register so that controller can grab it, and during read operation, disk controller will place data into this block so that CPU can pull it out. So it acts like bidirectional. Now let's come to our actual point. See, now we discussed that our device controller consists of three parts. The very first one is register. Now, see, these are, if you want to imagine these things as mailboxes. Like these are tiny slots which are used to exchange quick messages. We have seen this like CMD, stat, and data. CPU drops a command and say, okay, go find a file, check the status, and see if the drive is busy or not. And if everything goes well, it will actually grab a file or piece of data from this register. And we have already seen the different purpose of CMD, stat, and data. So this is specific purpose of register. Nothing but it will, what all things it will do? It have data, it has commands, and it also, if you want to write something, so you can use command register. For write only registers, or for you can use like command registers. So if we want to summarize it, like we could write tiny slots used to exchange messages. Okay. Now the second thing is staging area or the local buffer, which we depicted as SRAM buffer. So this is small patch of super fast memory right inside the chip, or like small part of RAM itself, which is right inside the chip or right inside the disk controller. While CPU is busy doing the other things, the controller silently fills this staging area in the background with data, and like it does piece by piece from the slow drive, and once it has a full batch ready, it hands it to CPU all at once. So CPU don't need to wait now. That thing is abstracted by this SRAM buffer. Did you get it? Like see, CPU are doing so many tasks, so it can't wait on like particular SSD or some SSD or some physical drive directly, so in order to write or read data, because in that case it will kill the CPU's time also. So what we have implemented is we have a buffer which silently will be pulling all the data piece by piece from slow drive, and in that particular time CPU will be doing its own task. And once the batch is ready, it will inform like CPU that okay, I'm ready, you can pull the data out, and CPU will pull, and the vice versa for read case. So the second one we just read is staging area or like local buffer. So what's its purpose is, so you can say it's like tiny memory of RAM itself in the chip. And what's its purpose? We already have read it. Now, the third thing is the translator or like interface logic. Although you might not see it here in the diagram. Okay, device controller. But it's actually present inside the device controller. Now, see, our computer's motherboard like to send data using like 8-lane highway, or if you just want to understand on high level, they send data parallelly, where like six, and if you want to go in depth, it sends where like 64 bits travel side by side. On the other hand, in case of our USB cable is like very narrow. It's if you want to consider it as a one lane highway or a serial data flow, where data must travel must travel in a single file. So this translator chip acts like some traffic police or traffic cop. So what it would do is it would rearrange all the 8-lane highway data into single lane so that data fits through the cable. So more like system bus produces data in a parallel manner. So it has data in a parallel manner, but our SSD cannot process data, like process so much of data whichever is there on the system bus. So it needs some sort of broker or some sort of medium in between which actually translate those parallel data into serial data for it, and that device controller having interface logic does it for SSD or like any physical USB cable. So this is, it's more like if you want to summarize, we can summarize in like it translates, for simple understanding, 8-lane highway into one lane. Using, it actually uses shift registers and all, but we won't go in that much of depth. Now it's time for a question. Let's say if you unplug your USB drive while the file is still in transfer state or the file is transferring, so why doesn't the CPU instantly crash and we see the blue screen? Why doesn't it happen? I'll see, we have studied system bus and we have studied device controller. The answer lies within themselves. So you need to think. I'll count for 5, pause the screen, think, and then we'll get the answer. 5, 4, 3, 2, 1. The answer is, see, we have already discussed that CPU isn't directly talking to the USB drive. It's talking to the device controller's register. And the controllers handle this physical disconnect by updating the internal status register, this status register, by what it does, it update that status register bit to error and politely tells the CPU later via software. So this process, when this process is happening, the CPU is completely insulated from the physical reality. So we won't get blue screen or the CPU won't crash instantly because it has been abstracted or it has been handled via device controller in a graceful manner. So this is it for device controller. The third thing we'll be studying is memory controller. So let's move on to that. So the third thing which we'll be studying is memory controllers. Now, before we even dive into the topic straight, let's first imagine a scenario. So imagine our computer's brain, which is CPU, is trying to read some instruction or read its next instruction, to be very precise, from the RAM, and at the exact nanosecond, the disk controller finishes its task of grabbing some data from a file, and it also wants to dump its bytes onto the RAM or its data into the RAM. Meaning, at the same instant, what if CPU and disk controller wants to do read or write operation from the RAM? Like on the exact nanosecond. So if we want to depict that situation, so for depicting that situation, let's try to draw a diagram. So imagine this is our CPU and this one is disk controller, and this one is RAM. So imagine CPU wants to write some data or command or anything, command or data. And this controller also wants to dump data whichever it has like done processing from the file. So it wants to dump it on the RAM now on the exact nanosecond. Now, what will happen if the board try to send electrical signals down the same highway or down the same wires at the exact same time, and we'll get, so in that case we'll get a massive crash, and that's called bus contention. What it will create? It will create electrical noise. It can corrupt our files in simple terms, and it can even cause our system to crash. So in order to prevent this collision, we need a very important component in our computer system, which is memory controller. And if we want to think, or let's first draw it. And if you want to think memory controller, so think it as of some strict sports referee which is standing right at the entrance of the RAM block, and what it would do is it would intercept all the incoming traffic from the CPU and the device controllers, and instead of letting them crash into each other, like whichever situation we have imagined, so instead of letting them crash into each other, what referee would do is the referee places all the incoming requests into a neat line called hardware queue. Basically, it will take all the incoming requests and it will put all the requests into a queue. So if you want to imagine this as a referee. Now if all the requests are going into queue, there should be certain way that like the request should reach out the RAM. So there should be some policy, and it actually depends device to device, OS to OS, which policies they are deciding. And usually what happens is the CPU is given the more priority, and then the high priority data like audio or some network package can take their turn, and later other things are managed too. And thanks to the rep free, that every component gets access to the RAM safely, one by one, without actually causing the chaos. Now it's question time again, but this question you need to answer from yourself. I'll just provide a question. You need to think, you need to research, and you'll need to get your answers, because we have read all the steps: memory controller, disk controller, and also the system bus. So the question is, imagine like if the memory controller always gives the CPU 100% priority or like top priority, what will happen to our network card during a massive CPU loop? So what will happen? Just think on it, research, and get your answers. If you want, you can comment it down in the comment box. So that's it for this video. Thank you. Keep studying, keep learning. We'll see you on the next video. Till then, bye bye.